Okay. All right. Good morning, everybody. Today we have our second lecture, and today we're going to study modeling of mechanical systems. As I introduced you to modeling last week, we discussed that the first step in modeling or controlling a system is to first understand how the system operates. And this means that we need a physical model that describes the behavior of that system in detail, so that we can now estimate the input-output relationship of that system. Or in other words, for any given input, we should be able to estimate the output of that system. And that's the objective of the next two lectures, is to design, is to come up with models that will represent the behavior of both mechanical and electrical systems. So we're going to split that into two lectures, and today we're going to do the first one on mechanical systems, and then we're going to do the next one on electrical systems, okay? And then try to combine them later. What we are going to see here is not necessarily new. It's something that you saw in dynamics before. We're going to go over it quickly and define a new notation that we use later. Establish the equation of motion for mechanical systems, and later we'll be able to solve them using Laplace transform. Okay. Just to remind you, I don't keep track of the chat because it's in a different monitor. So if you have any questions, feel free to just pause me and then ask using your mic. Okay. And if you're too shy to use your mic, maybe type your question, and if someone would like to read that on your behalf, that would be great. But if you have any questions, feel free to just interrupt me and ask. Okay. Yes.
Sorry to ask. I just have a question. It's related to the syllabus, I noticed.
Yeah.
Before. In the schedule, it says there's 12 labs, and then under the lab section, it says there's 11.
Lab section. So there must be 12. I'll double check. There's one per week for sure until the end. We typically have 12 weeks, and then the first week we didn't do it. I will double check, but I believe there are. I have to double check. There will be one per week. Yes.
Okay. I just wanted to point that out. Sorry.
Yeah. Thank you. Okay, so by the end of this lecture, you should be able to sketch a free body diagram of a mechanical system, use that to derive the governing equations of motion, and then understand the different types of input that we can give to that system. So let's start right away. The first thing we are going to model is the effects of inertia in a system. Any system, any mechanical system will have to be represented by a mass, which is an indication of the quantity of matter in a body. Mass creates inertia, which is a tendency to resist changes in motion. We are going to make some idealizations here. The first one is that our systems are rigid bodies. They don't deform under forces applied to them. Let's start with the first one there. We have a mass M, which is represented here by that block. We apply a force F to that mass, and the mass moves with a displacement X. So F is force, X is the displacement of that mass. What is the relation between the force and the displacement of that mass? How can we equate them? We can say that the sum of all forces acting on that mass is equal to?
Mass times acceleration.
Very good. Mass times acceleration, which is the same as mass times the second derivative of the displacement with respect to time. And the second derivative of displacement with respect to time. From now on, we are going to simplify our notation a little bit. Instead of writing the double derivative, we're going to use dots. So one dot above a variable means the first derivative of that variable with respect to time. Two dots, second derivative. So this can actually be written as mx double dot, where x dot equals to dx dt, and x double dot equals to dt. Okay, so sum of all forces equals to mass times acceleration. m times x double dot. If we could also write this in terms of speed, for example, how would we write this expression in terms of speed rather than mass? If we call the speed of this mass v, what would be the relation here? Would be equals to m times v dot, the first derivative of speed with respect to time, which is acceleration, or the second derivative of position with respect to time, which is acceleration. Okay. So this is a translational system. Now let's do the equivalent to a rotational system. So instead of a mass, now we have a inertia, a moment of inertia that we're going to call here G, a moment of inertia. Instead of a force, we now apply a torque. Here it is. And instead of displacement, a angular displacement, a linear displacement x, we have a angular displacement, which in this case is denoted theta. So instead of having the sum of forces, we now have the sum of all torques acting on this mass is equal to its moment of inertia, g, times its angular acceleration, alpha angular acceleration, or d theta dt, or a theta double dot, j theta double dot. Okay, so sum of all torques equals to moment of inertia j times acceleration, second derivative of position, angular position with respect to time, or theta double dot. And if you write this in terms of angular speed, let's call the angular speed omega. What would this become? Equals to j times
Omega dot.
omega dot. Very good. Omega dot. Now, first derivative of speed, angular speed in this case with respect to time. Okay. So this is the first element, is a mass. Any mechanical element will be represented as having a mass. Now we can attach to this masses other components such as springs and dampers to simulate the effect of friction. So let's start with our first element here, a spring. A spring is a system that is supposed to store, is designed to store energy. We're going to make an ideal assumption about this spring. It's a ideal spring. It has no mass and it has no friction. It's simply an elastic element. A spring has a coefficient that gives the ratio between deformation and force. So that's the stiffness constant. That's K. That's the stiffness constant. And we have the displacement of the spring on each side of that spring. So if we had, let's say, a spring like this that is attached, one end is attached and the other end is stretched, what would be the force developed in this spring as a function of the displacement? And assuming that the coefficient of viscous, coefficient of stiffness is K, we have the force being equal to K times X, the stiffness constant times its displacement. Right? This is valid when one end of the spring is held and then moves. What happens if now both ends are moving? I'm stretching one end one way and one end the other way, or even the same direction, as we show here. We have one side of the spring is displaced by x2, the other side of the spring is displaced by x1. So what is the new force now developed in the spring? F of t equals to the stiffness constant times the relative displacement between both ends of this spring, that is x2, the displacement in one end minus the displacement in the other end. Okay. X is the displacement, that's the unit is meters, force is newtons. So what is the unit for K? What is the unit for K, the stiffness constant?
Newtons over meters.
Newtons over meter. Very good. So this is the unit for K. When you multiply that by the displacement, we get Newtons, the unit of force. This is the case again for a translational or linear spring. Now let's take a look at a torsion spring. So torsion spring, instead of stretching, we're going to twist it like that. And the stiffness
Sorry,
constant.
can I ask a question before we move to the other one?
Yeah.
So x1, when we say x2 minus x1, that's because we're doing it algebraically. So we're actually adding the two together in a way.
Yes. Yes.
Oh,
Well,
okay.
we need to. One end of the spring doesn't give you enough information to tell you how stretched that spring is. We need to look at the other end as well, right? So let's say if you move x1 and x2 by the same amount, the spring doesn't stretch at all. There's no force.
Oh, I see. Thank you.
Right? If you move them in opposite directions, then you're moving these, you're stretching it by 2x2 because x1 is negative x2.
Thank you. Got it.
Yeah. Now let's go to the torsion spring. So for the torsion spring, we have an angular displacement and we have a torque. So now the relation becomes torque equals to K times theta 2 minus theta 1. And you may ask, why not theta 1 minus theta 2? Well, if the torque is applied on that end of the spring, we can assume that theta 2 will be greater than theta 1. But if we switch it, it doesn't matter. We just get a negative sign later in the equations that will tell you that the displacement actually occurred in the other direction. So all we need to do is to be consistent with the units. So what is the unit for K now? Theta is in radians. The torque is in Newton meters. What is the unit for K? The stiffness constant. Newton meter per radian. Okay. So that's the spring. Any questions about the spring? Nope.
Would you be able to go to the last slide quickly? I missed. There you go. Cool.
All good?
Yep.
Yeah. All right. So let's move on now to the third and last element we need, which is a viscous damper. And here I would like to emphasize the viscous, the word viscous here, because you're not dealing with static friction. We have a viscous damper that is here to dissipate some sort of energy and simulate or capture the effect of friction. This is different from static friction. Static friction, if you want to, let's say, push a box that is on the floor, you need to apply a certain force before it starts to slide. Right? That threshold is a static friction. We are dealing with the viscous friction. So that begins when the box starts to slide. And then the faster you go, the more force appears in the form of friction, the higher the pushing. Right? That's that relation between the force and the speed is the viscous friction coefficient, not a static friction. Okay, so viscous dampers or friction always dissipates energy, and we are going to make an assumption again, is that there is no mass and there is no stiffness. This is a purely viscous element. If we want to add mass or stiffness, then you need to combine this with the previous elements we saw. So here is the symbol for a damper, which again is simulating friction. And we know that the speed, the force becomes proportional to the speed, and that proportionality constant is B, is the viscous friction coefficient. So in this case here, if one end of our our damper has a displacement x2, that means that the speed is x2 dot. The other end has a speed displacement x1, which means a speed x1 dot. The force developed in this damper is b times the relative speed between both ends, x2 dot minus x1 dot. Or v2 minus v1, the speed on each side of the damper. If we fix one side of the damper, let's say x1 becomes fixed, then x1 dot becomes 0, that there's no speed when you're fixed, and then the force simply becomes b times x2 dot. If we go to a rotational system now, we have the same idea, but now instead of angular speed, linear speed, they have angular speed, and the torque developed in this damper becomes b times theta 2 dot minus theta 1 dot, or b times v2 minus v1, b times omega 2 minus omega 1, where v and omega are the linear and angular speed, respectively. And again, I would like to emphasize here the difference between viscous friction and static friction. Right? Static friction is not a linear phenomenon, and that therefore cannot be accounted for in our models. We only deal with dynamic systems that are linear and time invariant, which means that we cannot account for the static friction, only viscous friction in our simulations. Any questions so far?
What are the units for B?
Well, let's see. Good question. So in the top one, we have a speed that is in meters per second. We have a force that is in newtons. So what should be B? What should be B? Should be Newton second per meter. All right, so that when we cancel everything out here, we end up with newtons. So that's for the linear case. Let's do the angular case. So the angular case, we have the speed is, 1 second, the speed is radians per second. Torque is Newton meter. What is the unit for B? Newton meter second over radians. Radians we don't need to add there. There's no unit, so divided by radians, if you want to have it there. Okay, and that's the unit for B in a rotational system. Okay. All right, so let's do an example here. Here I have a muscle that is holding a weight. The muscle can be modeled as a spring and a damper in parallel. The spring simulates the elasticity of that muscle, and the damper simulates friction happening in the muscle. And we can put them in parallel. What is the equation of motion here if we apply a force F of t to that muscle? Let's forget about gravity for now. Let's assume that we only have that force as the input. Well, we can attach a spring and a damper to the system. The spring has a stiffness constant K, and the damper coefficient B. Now let's do the free body diagram of this system. For the free body diagram, we can take the mass and detach everything that is connected to it, and then replace those elements with their respective forces, the forces that they exert on the system. The first one is the input force, F of t, that is pulling the system down. We have now two forces pointing up. So if the mass goes down, the spring is trying to push it back up. So the effect on the mass goes up. And the damper does the same job, is trying to pull it back up. So from the mass perspective, there is a force going upwards, resisting the motion downwards. So there's another force like that. Let's assume here that our displacement goes downwards, and let's call that x of t. So now what is the magnitude of these two forces? What is the magnitude of the spring force, the first one there?
F of t minus the what was it called? Force of the damper.
Well, let's put it this way. That would be the net force. Let's just talk about the spring. What is the spring doing on the mass? What is the effect of this? Only the spring on the mass. If it's attached to the mass is attached to the spring and you pull it down, we are stretching the spring. So the spring acts on the mass. And what is the magnitude of that specific force? Wouldn't that be K times X, the stiffness constant, times the displacement of the spring? Right? That's the one force that comes from the spring. What about the damper? If we do, what is the force exerted in the damper now? Or let's put it this way, maybe that's why you got a bit confused. What is the force that the damper applies to the mass? Let's put it that way.
Wouldn't it be the weight of the mass?
Wouldn't be the
Weight of the mass, that the opposing weight. So
the weight of the mass does have an effect, but we are not considering gravity, right? Let's just forget about gravity. My question is this: let's go back to the spring. I have a mass connected to a spring. If I move the mass downwards, the spring applies a force to the mass. What is the magnitude of the force that the spring applies to the mass? It doesn't depend on the mass. It doesn't depend on how fast the mass goes. Only depends on how much stretch that spring is. So this K times X. Okay. Now let's talk about the damper. What would be the effect of the damper?
The damper's force equation would be B V2 minus V1.
Right. So it would be B times the relative speed of each side of the damper. The speed at the bottom is X dot. And the speed at the top of the damper is 0 because it is fixed. Right? This means that the damper is fixed.
Sorry, what exactly is X?
X is the displacement of the mass. X dot is the speed of the mass. Okay, Kx is therefore the magnitude of the force applied by the spring. B times X dot is coefficient of viscous friction of that damper times the speed of the mass, that is the viscous friction force. So this is the free body diagram. Now that we have all forces acting in the system, see, we replaced all the elements with their respective forces that they apply to the system. We can do the sum of forces equals to mass times acceleration, which is X double dot. Now we need to define a positive direction. Let's assume that the positive direction is pointing upwards. So all forces pointing upwards are positive. We could do it the other way. I could do it downwards. Let's do downwards because that goes along the acceleration. Let's do everything pointing downwards is positive. So what do we have? Sum of all forces. If it points down, that's positive. What else? Minus Kx minus Bx dot equals to Mx double dot. And this is the equation of motion for the mass spring damper system. Is simply a differential equation. Sum of all forces equals to mass times acceleration. Any questions here?
What's the unit of X?
Meters.
Okay.
Meters. Displacement, I'm going to measure that in meters. Anything else?
Yeah, can you quickly explain like what the damper does again? Does it just oppose the motion?
The damper is simulating friction. Let's put it this way. I could have represented this mass like this. I could have added a surface here, a surface. And this mass, as it moves up and down, it touches that surface, and there is friction between the surface and the mass. And the friction coefficient here is B. So that will create also, if the mass moves downwards, it will create a force pointing upwards. We can replace this with a damper. The damper simulates friction inside of the muscle. As we stretch it faster, we'll see that it becomes harder to stretch it. If you go slowly, and if you go faster, it's not the same force. Where is that coming from? Well, it cannot come from the spring, because the spring only depends on the displacement. So if there must be a viscous friction element there that increases the force, the faster you go. This relation between speed and force is the damping friction coefficient.
Sorry, Professor. Why would you want the force to be less? Like, isn't more force desirable?
Why would I want the force to be less?
Yeah, by using a damper.
It's not up to us to decide. That's the physical structure of the muscle. That's how it is represented, how it works. What we are doing here is that we are capturing that phenomenon using equations, using a damper. Right? If we didn't have the damper there, it would mean that the system would be purely elastic, which is not the case. If the system is purely elastic, there's nothing dissipating energy. From the moment where we stretch something and let it go, it would just oscillate and never stop. But the damper dissipates the energy and then eventually makes the muscle stop. So there is a fundamental element of this system.
Sorry, can I ask a question? Did you say damper, and the difference between damper and friction is one of them is linear and the other one isn't?
The damper captures the effect of viscous friction, which is a linear phenomenon. The damper cannot be used to capture the effects of static friction, which is not linear.
Oh, thank you.
So damper means viscous friction, and let me just mention the static friction here because it's a non-linear phenomenon that we cannot account for because we have to limit our systems to linear systems.
So what's the difference between viscous and kinetic friction? Or are they the same?
They are the same.
Okay, cool.
Anything else?
Yeah. So you said f of t minus kx minus b x dot equals to m double x. So how did you get that part? Like, I understand where the f of t is, the kx, which is which is from the elastic or like the spring, and the bx, which is from the damper. But where's the m double x from?
What is the mx, the x double dot?
Yeah.
That's mass times acceleration. That's the very first equation we had here. Right? There, sum of forces, this is Newton's law. Sum of forces equals to mass times acceleration.
Okay. Oh, I thought you said we were not taking into account acceleration and gravity.
No, we're not taking into account gravity. That doesn't mean that you're not taking into account. Those are different things.
Oh, okay.
Okay, we cannot write this equals to 0 because that would mean the system has no mass. So we do need to account for the inertia. All right, so let's move on to example 2. We have a spring-loaded knee brace, which is a non-surgical approach to pain reduction. So I think the picture must be showing better on your end there. It's a device that attached to the knee and it has a spring that can help people walk. They are designed to act like a car suspension system to increase the stability and reduce pain and compression in the knee joint. Find the differential equations that describe the angular speed of the knee as a function of the user input torque. All right, so we have a system attached to the knee Our input to the system is a torque that we apply. And now there are two things acting against or along that torque. There is a spring and there is a friction coefficient that comes from that device. How can you model this system? Well, if you want to model the lag, if you want to model the lag as a dynamic system, we need a mass, and the mass has an inertia, and this inertia we're going to call that J. The brace has a spring. The spring compresses and stretches. It's an angular spring. And there is friction in the system as well. They're going to model here as being a coefficient of viscous friction B along the surface of contact between the brace and the line. The torque that we input the system, let's call that capital T. So what are the forces acting on this? If we are applying a torque, let's say clockwise, the spring will act against it, will act counterclockwise. So there will be a torque from the spring acting in the opposite direction. And there will be friction also acting in the opposite direction. So we have two torques acting against the torque that we put to the brace. What are the magnitude of these torques? Let's start with the spring. If the displacement of this mass is, let's call this theta, and let's give the coefficient of this, the stiffness of this mass, the stiffness of this spring, let's call that K. What would be the magnitude of the torque as we now turn that mass? Would it be K times theta? And what would be the viscous friction coefficient? Sorry, the viscous friction torque would it be B times
theta dot.
Theta dot. Very good. B times theta dot. Now we can write the equation of motion by summing all the torques and equating that to J theta double dot. So sum of all torques equals to J times theta double dot, which is alpha, the angular acceleration. What torques are do we have here?
So in this situation, the mass observing the viscous friction would be like the knee, like being held back by ligaments or tendons or something, right? Or
Yeah, so let's say we have a system like this, and then this is one side of the brace, this is the other side, so it moves like that. All right, there is a spring here, and there's also friction between these parts, these moving parts.
right.
It could also be the internal friction that we have in the bones. Could be also part of that friction.
Cool.
All right, so some of torques. Yeah.
Sorry. So one side of the spring is attached to one side of the brace, and the other one to the other side. It's like
Yeah.
it's like horizontal between them, right?
Let's assume that here we have the brace. This part is fixed, and this part moves.
Yeah.
Right?
Yeah, but like, how's the spring placed between them?
The spring is just connected between the fixed part and the moving part.
Okay, thank you.
Okay, so what is the sum of torques here? Now we need to define a positive and negative direction. So let's do anything that goes clockwise. Let's make that positive. So anything that goes clockwise is positive. There's a convention that we are choosing. So sum of all torques is the input torque T. We define here everything is given in the same direction as the input torque. So plus K theta plus B theta dot equals to J theta double dot. This is the equation of motion for the brace. Now notice that the problem asks for the relation between the angular speed and the torque. So now how can you rewrite this expression now in terms of angular speed instead of position? How would we do that? Here we have position. What is the relation between position and speed? Let's say torque is torque, the derivative, right? So K is still the spring constant. What is the relation between theta and the speed omega? So we have
the integral.
Would be the integral exactly of the speed plus b times the speed itself, that's theta dot, plus j equals to j times the speed. First derivative of the speed, which is the same as theta double dot.
Sorry, Professor, is that like t plus k, like, and then the angle plus b, then angle dots? Is that t or j?
The very first one is t and is equal to j theta double dot.
Okay. And then t is the
T is the input torque that we apply to the brace.
Okay. And how come that's in the same direction as K and B? I thought it was in like opposite direction from
Yeah,
like drawing.
All right.
Yeah.
Yeah, so we can make them in the opposite direction depending on the cycle of motion. Put them in the opposite direction. What are the differences? Difference would be that these two signs would become negative. And if they act against the torque, which is more accurate to be fair, then those two signs will become negative.
Thank you.
Okay. Anything else? No? All right. Okay, so now that we have a system and we have the equations for that system, we need to define the input-output relationship. We need to find the output for a given system. That's our ultimate goal, is to find the output for any sort of input. And we are limiting our system to linear time invariant systems. That means that we have to respect three conditions: homogeneity, superposition, and time invariance. We discussed that in the last lecture. Going back here to the example from last lecture, if the system is linear and a input x1 creates an output y1, then if we scale the input by a factor of alpha, the output will also be scaled. Now that's the system, this is a homogeneous system. Superposition means that if the system creates an output y1 for an input x1 and creates an output y2 for an input x2, when you apply both inputs to the system, what is the output of that system? Is the sum of each output, y1 plus y2. In other words, we can see the system as having different inputs, and the output of that system is the sum of every individual output. And the last condition is time invariance. Time invariance meaning that the system parameters do not change over time. If you apply an input to the system at time t, or t 0 seconds from now, the outputs will be the same, just shifted over time. And there is a typo in the lecture notes. This should be negative instead of positive. So back to the example we had in the last lecture. Let's say we have a bell and we strike that bell at time 0. The result, the output of that system, is a sound that decreases over time. If we now strike the bell at 1 second, the result is the same, but now the sound starts at 1 second, not at 0. If we do the bell strike the bell at 0 and 1 second, then the output is the combination of both strikes, is one output plus the other output. So we can take our system, when you look at the input like that, 2 strikes. If you know the response for 1 strike, we know the output of the system for a undefined number of strikes, because it's simply a linear combination of that same input. This is to say that if we know the response of a system to a given input, to a simple input, we can define the output of the system for any combinations of that input. So let's now define this input that we need in the system so that we can calculate any outputs. This is the impulse response, right? That's what you are looking for, is the function called the impulse function. The impulse is a function that has a unit area like that happens over a small period of time, and this period of time tends to 0. So as the period of time delta t tends to 0, then this height tends to infinity, right? The area under that curve is unit, and that's what we typically call the unit impulse. And let's assume that this system creates that output. When you apply this unit step to the unit impulse to the system, it creates that output. If we now have a different input, let's say an input where we turn something on and hold this value for a longer period of time, we can define this input as a combination of several input functions, or a sum of infinite input functions that will form this new shape. And the output of our system is simply the combination of all these outputs added together. The difference is that the first one will happen at time equals to 0. The second one will happen shortly after that. The third one shortly after that, and so on. When you make delta t tending to 0, now you have an infinite number of impulse functions, an infinite number of outputs that are result from each of these inputs that are shifted over time. They're happening one after the other. We take all these outputs, when you add everything together, this is the response of the system to that input, right? So this is to say that to know the output of a system, all we need to know is the response to a unit step input. I'll get into more details soon. So how do you define mathematically this function? Well, this function is the Dirac function, or the delta function that you're probably familiar with. Is defined mathematically as 1 over delta t when time equals to time is greater than 0, and delta t here tends to 0. We can rewrite this expression using a to have a unit impulse here. Just multiply both sides by delta t, and this is the definition of the Dirac input function. Let's go back to our example here. Mathematically, what we can do now is to take a combination of this input, apply that to the system, see what you get in the output, and then add everything up. So let's assume that our input is something like this. Let's say a signal. One second. It's a signal over time with value, and then it goes down. We can form the signal by a bunch of impulse functions put together, squeezed together. The first one happens at time 0, the second one happens at, say, 0.01 seconds, and so on, so on. If you only had the first one, then the output of our system would be the response of our system at 0 times the input function that we just defined. But now we have one happening delta t seconds after that, so we need to compensate for that and add that as well. So plus the response at time delta t, and time the input function again. Now you see it is shifted over time by a factor of delta t, and plus all other elements. that compose this input function. And now we add everything together. This is what this fancy sum is doing there. We're just adding the result of every individual impulse response that happens at a given instant in time. And you can keep going. If we now have, we don't need to worry too much about this, just want to show you that if now this delta t becomes very, very small, we can rewrite this expression in the form of an integral. And this integral is what we call a convolution integral that you probably saw in calculus before. And the convolution integral now gives us the response of the system to any input defined as a combination of impulse inputs. Now, don't need to worry about this. I just want to, with this, tell you that there are different types of inputs that we can apply to this system. The first one is the impulse function. So the impulse function is a pulse that we apply to the system, like a hammer is striking a bell. We can have a second type of input, which is a step function. A step function is something that at time 0 goes to a fixed value and stay at that value on and on. That could be, for example, when you apply a voltage to a circuit, we turn on a switch, that a voltage is applied and held at that value. That's a step function, which can again be a combination of several input functions, several impulse functions. Now, do we need to go through all this every time we want to calculate an output? No, we don't, because we have tools using Laplace transform that we're going to see later that will allow us to just apply the properties that we saw there to calculate the output of a system for any type of input, if we know the input function. A ramp function is another one that is typically used. Let's say we have a water tank that is filling up with water. The more, as time goes by, the water pressure at the bottom of the tank increases linearly. So that's a ramp. It's not a step because it's not constant. It's not a pulse because it doesn't just appear and disappear at time equals to 0. It keeps going up slowly. And we have the third type of input that we could add to the system is a parabolic function. It's just now a force, for example, that increases non-linearly over time. We could also have sinusoidal waveforms, etc. But for now, let's concentrate on this form. These are the types of inputs that we can apply to our systems.
Sorry, Professor.
Yeah.
What was your example for the step function, like in a real life scenario?
Yeah, I'll give you more examples in this slide here.
Okay.
So let's summarize that. The impulse is a high pulse applied to a short period of time. For example, a hammer striking a bell, or a mass spring damper system that has where we slap that system. We apply a very high amount of energy to it to create some sort of motion, and then you remove it. A step could be a voltage applied to a system that is held constant. Turning on a switch, for example. For example, you have a light, a lamp. When you turn on the switch, you're sending energy constantly to the light, to the lamp, and you're holding that value constant. So that's a step input. Or, for example, in the mass spring damper system, I'm pulling on the spring on the mass and then holding that value constant. The force I'm applying to hold the spring stretched is constant. That's it. Okay, and a ramp would be, as the example I gave for the pressure in a tank, which is filling up. So we now have a pressure at the bottom that slowly goes up over time. That's a ramp input. Here I have other examples. Let's, for example, consider a thermometer in a room temperature placed in a patient's mouth. What kind of input would that be from the thermometer's perspective? We take the thermometer, the temperature will change. The temperature is the output. We are taking the thermometer and putting that in the patient's mouth. What kind of input are we giving to the thermometer?
Step.
Step. A step. Very good. A step function. A surgical robot tracking a target moving at a constant speed. What kind of input is that? We have a surgical arm that is tracking something that moves with a constant speed. What kind of input would that be?
Step again?
If we are controlling the robot to follow the speed, it would be a step, indeed. What if we are controlling the robot to track a position? Then the target position keeps moving, keeps increasing, right? That would be then a ramp function. If you tell the robot, go at 5 millimeters per second, then the robot will just start moving at 5 millimeters per second. That's indeed a step. If we now tell the robot, move along this trajectory that is increasing over time, follow this thing that is moving at a 5 millimeters per second. So point 1 will be here, at time 2 will be here, at time 3 there, and so on and so on. Our position, our reference position keeps moving and increasing over time. That would be a ramp.
So
Right,
this
but
one actually is tracking the distance, right? Then it is a ramp.
Tracking the distance would be a ramp. Keeping a constant speed would be a step.
Okay.
But why would, even if it's tracking the distance, it's still moving at a constant speed. So the robot itself will just move at the same speed following it. So why would it be ramp?
From the position's perspective, it would be a ramp because the position, let's plot here. If we have time here and position, it would go like that. If this was the speed would be constant. All right, so once you reach that speed, we just stay at that speed. If you now want to go to control the position of the robot, from the position's perspective, the robot is doing exactly the same thing. But from the position's perspective, the position keeps increasing. Our target is always moving over time. All right, so that would be a ramp. A artificial heart pump turned on. If you want to control blood flow, for example, what kind of input would that be?
Impulse?
If we turn on to control the pressure and we want to maintain that pressure, we need to apply a step.
Yep.
Right? We need to apply a step. A injection of a pill as input to the body.
Impulse?
Here we can argue both ways. We can say there's either an impulse or a step, depending on how we see it. If the action occurs fast and disappears, then it is an impulse. If apply something that has a permanent effect, then it would be more like a step. So this one depends on how we see the system. Okay, so all these input signals, the important thing to remember here from all these calculations that I tried to show you is that they are a combination of impulse responses of the system. And we do those calculations using the convolution integral. We are not going to do that analytically. We'll use tools. Luckily, somebody else has done that for you. And we'll just use those tools later to take these inputs, apply to the system, pass that through the models we created, pass that through these models, and get the output we want for a given input. So that's our ultimate goal, is to calculate the output of the system for any type of input. Now you're going to do that in lecture 4, looking at a Laplace transforms. Okay, let's do a few exercises. Let's start with this one here. I'll let you read it as a screen board here that I was supposed to do before we started, but I had some technical problems. So here we have a tiny micromechanical resonator that allows the core of implantable devices for monitoring and treating aneurysms, a leading cause of heart failure. Pressure changes deflect the transducer's diaphragm and shifts the mass resonance frequency, which can be monitored externally.
Are you writing on like a board right now? Because we can't see if so.
No, I'm just reading and raising the board right now.
Okay, sorry.
That's okay. An equivalent model of this sensor is shown below as a mass spring damper system. Write the equations of motion for each mass. So here we have two masses. They are connected through two springs. The input to that is a force F of t. And the output, we're going to define as being the displacement of each mass. So now we are interested in the equations of motion for each mass. What should we do first? What should we do first?
Draw the free body diagram.
Very good. First things first, replace all these elements that are connect the masses with their respective forces. That is, create the free body diagram. So let's do that. You guys can see my my thing here. And we have these two masses. Let me just move something.
I'm sorry, can you please show the question again for like 1 second?
The question is create the equations of motion for each mass.
Yeah, can you please show this slide for like a second so I can just take a picture of it? Thank you.
Yeah. All right, so let's start with mass 2 right there. We can create the free body diagram for mass 2. So this is mass number 2. What forces are acting on this mass? Let's put all of them here. What forces are acting on this mass?
The spring and the FT.
The spring and FT. So we have FT, and we have the spring. In which way is the spring force going? Is going back. Let's say we move this mass, the force is going to the right. If the mass moves to the right, then this spring here opposes the motion of that mass and applies a force to the left. Right? Let's define the displacement of our masses. Let's assume that a mass 1 and a mass 2 have a displacement of x2 and a displacement of x1. Now, because the force is going to the right, then let's assume that they are both going to the right. Which one is greater? Is x2 greater than x1 or not? Or is x1 greater than x2? If the mass m2 moves to the right, then we can assume that first mass m2 will start moving before mass m1 starts moving. So let's assume for our calculations that x2 is greater than x1. And let's further assume that anything that moves or that applies a force to the right is positive. That's the assumption we are making. We could switch this if you want. That's an assumption. We just need to be consistent. So what is this force here? If mass m2 moves to the right, this force goes to the left. And what is the magnitude of this force? This force represents this spring. What is the magnitude of that force? Is K2 x2 minus x1. Now x2 is a displacement on this side of the spring. x1 is a displacement on the other side of the spring. Why not x1 minus x2? We could do that, but our assumption here is that x2 is greater than x1, which means that this is positive. And if this is positive, then the direction we have here specified as pointing to the left is correct. If you wrote x1 minus x2, according to this would give a negative number, which indicates that it would then have to revert the direction of that arrow. Anything else acting on this mass? No, that's it, right? So now we can write the equations of motion for mass 1. So that is mass 2, sorry, that's mass 2. We have sum of all forces acting on the mass equals to m2 times x2 double dot. Mass 2, acceleration of mass 2. What are the forces acting on this mass? F of t is positive because it points to the right, according to our definition here, minus k2 x2 minus x1. Those are all the forces, m2 x2 double dot. Okay. Now let's do mass m1. Any questions about mass m2?
Yeah, I just had a question.
Yeah.
The question is saying that there's a mass spring damper system. So where does the damper apply in this?
Where is the damper? I don't see any damper. They don't see any damper. Yeah, right. Yeah. Don't. Let's just assume it's a mass spring system. Once we are done, I will add a damper, and then you'll see what the damper would have done. Okay.
Okay. Thank you.
So mass m1 now. What is acting on mass m1? We have the same force here, the same force from this spring, but now it's going in the opposite direction. If mass 2 moves to the right, it is pulling on mass m1 to the right. This spring makes the mass move to the right. So here it is applying a force in that direction. If mass 1 moves to the right, then this spring is holding the mass and will apply force to the left. What are the magnitudes here? What is the magnitude of this force?
K2 times x2 minus x1.
Exactly the same as above, right? We cut it halfway here. So the force here and here must be the same. They just have opposite direction. So this is K2, x2 minus x1. And this one here, what is the magnitude?
K1, x1 minus x2.
Let's see, both ends of this spring are moving, or just one. So this end of the spring moves, this one is fixed.
Just the x1, wouldn't it?
Would just be x1.
It would be K1 x1. Right, because this side here is fixed. So for mass 1, what do we have? Sum of all forces acting on mass 1 equals to m1 x1 double dot, which is positive negative K2 x2 minus x1 minus K1 x1 equals to m1 x1 double dot. Any questions? So somebody mentioned what happened about the damper, that it was supposed to be there and it's not. Well, let's add that damper somewhere. Let me see. Let's put the damper. It's hypothetically. Let's put the damper here. It's well behind K2 there. What if the damper was here? It's not very clear, is it? What happens now? Let's just hypothetically add a damper there. And let's see that this damper has a coefficient of viscous friction B. What would happen? The damper would create a force slowing down this mass. It would need to add a force here. What would be the magnitude of that damper force? Bx2 dot minus x1 dot. And if it acts here, it needs to act there. So the damper would go this way and would be Bx2 dot minus x1 dot. Now we are basically adding these two elements from that. And then we would have another term right here, another term right there. What would be the term here? Would be plus bx2 dot minus x1 dot. It would be positive or negative for mass m2. The damper would be holding the mass back, so it would be negative. And the damper would be accelerating mass 1, so it would be plus x2 dot minus x1 dot. If we added the damper there.
Hi, I just have a quick question out of curiosity. Does the direction of opening for the damper mean anything, or is it just
No,
kind
it doesn't.
Okay, awesome. Thanks.
Okay, any questions here?
Don't we also have to add the damper between M1 and the wall or whatever that is?
Well, we can.
Like,
Yeah, we could add another damper here if you wanted. I'm just adding this as an example, but there are no rules. I could have just put it there. It's just a bit more complicated there.
So it doesn't mean that we have to add the damper wherever a spring is.
No, not necessarily. No.
Thank you.
Yeah. Okay. Any other questions?
I just have a question. So was it a mistake that the question said spring
Yeah.
damper?
Yeah, that's a mistake from my end.
Oh, okay.
So if we did
regularly,
regularly, you the diagram is provided.
Okay, thank you.
Yeah. Okay, so
Other
this
than
doesn't
like
need
a,
to be there.
go ahead.
Yeah. Go ahead.
Other than like a wall acting as like, or adding friction, is there like an example of like a mechanical damping device?
A damper in a car, for example.
Right.
Yeah, the damper in a car acts exactly like that.
Like a air shock or something.
Exactly. Yeah. Yeah. Anything, or even if you want to move something in the water, for example, the faster you go, the harder it gets to move it.
Right.
Right, and that's friction. That's viscous friction there as well. Right, that we can represent as a damper. All right, so if there are no other questions here, let's do another one. Let's do exercise 3. No, actually, let's do exercise 6. It's more interesting. Let's do exercise 6. I will just erase here what I made, and I'll let you guys think about this one. They start by creating the free body diagram for each mass, and then we are going to solve it together. So you have, the objective is the same, just find the differential equations for each mass. The only downside of a whiteboard is that it's very hard to clean. So but in the meantime, see if you can identify which forces act on each mass, in which direction they act, and what their magnitudes are.
Sorry, by the way, do we get the answer to the other exercises that we won't go through in this lecture?
Yes, I will either provide them in the written or a link to a video. If you notice, in this lecture, every exercise has a link. It's a solution to, there's a link to YouTube, and then I recorded a video and it's posted there.
Oh, yeah, I see it. Thank you.
Yeah, and if there is no video, then I will just write the data in the PDF and then post it later. So there are a few exercises. Try to solve some of them on your own before you look at the solutions. It'll give you an idea of how you're doing. There's a lot to practice there, right? But some of them maybe do a few more with help, and then attempt a few on your own. Okay, so this is the new system we want to model. What is happening here? What is different? Well, we have still two masses, but there are some key changes. The first one, if you notice here, is that there's another spring there, and we are applying displacement to the spring. Why not a force? Could we have a force here? We can't. The functions, a spring doesn't have a mass, so we cannot apply a force to something that doesn't have a mass. That's why the input is a displacement to the spring. So we are moving the spring towards one end. Spring is connected to this mass. Look at how this mass slides on a plane now. And there is friction. There's friction between the mass and the plane. Friction coefficient B. Mass M2 connects to mass M1 through a spring. Mass M1 has this role here to say that there is no friction between the mass and the plane. And this mass is attached to a spring and a damper connected to a fixed frame. So let's start with mass M2. Let's start with the free body diagram for mass M2. Tell me which forces are acting on this mass. We have, if we are pulling on x of t towards the right, we have a force here making this mass move to the right. The mass is attached to another mass through a spring, and this spring is holding the mass from moving to the right, so a force to the left. And what else? As the mass speeds up and starts to move to the right, friction occurs between the mass and the sliding plane. In which direction is that force?
Left.
To the left. Of course, to the left, because friction always opposes motion. What are these forces now? What is the magnitude of this force? This force is coming from this spring, so it depends on how much this spring is stretched. Let's call the displacement of this mass here x2. Let's call the displacement of this mass x1. What is the displacement of this spring? What is the compression of that spring?
KF2
Is?
K3 x
K
minus x2.
Exactly, very good. K3x minus x2. Excellent. Displacement on one end, displacement of the other end of that spring. K3x minus x2, and this is the magnitude of the force making mass 2 move to the right. Now let's move to this one here, which is due to this spring, K2. So what is the magnitude there?
K2 x2 minus x1.
Excellent. K2 x2 minus x1. Now assuming again that x2 is greater than x1 and x is greater than x2 greater than x1. Now if you move this way, this mass starts moving before that, so you can assume that x2 is slightly greater than x1. Eventually they balance out, but so we can define the signs as being positive. Now what is this force? This force comes from viscous friction coefficient here, B. What is the magnitude of this force? There's a trick there. What is the magnitude of that force? Any guesses?
B times x2 dot.
B times x2 dot. Very good. Excellent. Why is this not x2 dot minus x1 dot?
Because it only depends how much M2 moves on the surface.
Exactly. It only depends on the speed of the mass with respect to the surface. If this damper was between the two here, connecting the two masses, then yes, it would be x2 dot minus x1 dot, but it's here is only between M2 and the surface. Excellent. Pretty good. Okay, anything else acting on this mass? No? So let's assume our positive directional forces. Let's say that anything moving to the right is positive because the mass is accelerating to the right is more convenient. Sum of all forces equals to M2 x2 double dot. What are these forces? Positive, negative, negative.
May I ask why it is just b times x2 dot and not b times x2 dot minus x1 dot?
Because we are only dealing with this element, right? The acceleration of each mass does not depend on the acceleration of the other mass. It only depends on the balance of forces acting on that specific mass. So when dealing with M2, we need to take away M1 and just balance the forces on M2. When you do M1, we only look at forces on M1. How fast M2 is, what M2 is doing, well, it will show up indirectly here by its speed and displacement, but not its inertia does not affect the other.
Okay, thank you.
Okay. So K3 x2 minus x1, positive because it goes to the right, minus K2 x2 minus x1 minus b x2 dot equals to M2 x2 double dot. Okay, and this is the first equation of motion. This is for mass 1, or mass 2. Sorry, this is mass 2. Let's do mass 1. We are already running out of time as usual, so let's do mass 1 quickly. Tell me what forces act on mass 1. We have one force here to the right. Where is this coming from? This is this force, this spring, making mass 1 moving to the right. What else we have there?
One going to the left for the damper and one to the left from the other spring.
Excellent. One for the damper and one for the spring. Now let's deal with their magnitudes, starting with this one. What is the magnitude of that one? What is the magnitude of this force that comes from this spring? Displacement of the spring times the relative compression of the spring, x2 minus x1, which is exactly what we had here. Right? If you connect these two masses together, these two forces are replacing the spring, so they must be equal, but in opposite directions. This one is for the damper. What is this force? B times
x1 dot.
x1 dot. Excellent, x1 dot. And what is this force from this spring?
Just k1 x1.
A1 into x1.
K1 x1. Excellent. Now let's do the sum of all forces for mass 2. Sum of all forces, sorry, mass 1 equals to m1 x1 double dot. Positive, negative, negative, according to our convention there. K2 x2 minus x1 minus bx1 dot minus kx1 equals to m1 x1 double dot. And this is the equation of motion for mass. Okay. So it's not as hard as it seems at first glance. You see that it's pretty much the same procedure every time, and it gets easier and easier with practice. So there are in this lecture there are 6 examples. We solved 2 of them. The remaining 4 examples, I believe all of them have a link to the full solution, but exercise 2. And exercise 2, it doesn't have the solution there. I'm going to add it to the notes and then post it later. But for the other ones, you see a link to a video where the solution is explained there. And then, as I mentioned, try to do them on your own. If you need one more example, go through the example in the video, but keep at least one or two of these examples to be tried on your own and see how you're doing with the solutions. Any other questions here before we wrap it up for today? We are already 5 minutes late. No?
So when you're writing on the light board, are you writing backwards?
Well, that's solution number 1 is to write backwards. Solution number 2 is to invert the camera on. Camera view, right? That is a bit easier.
Cool.
Yeah. Any other questions?
Yeah, I wanted to ask, is there usually only one damper for a system, or can you add multiple? Because I feel like that would make things.
We can add as many as needed to capture the dynamics of that system. Okay. Here, we already make an assumption about how the system behaves because you're given the model. But if I tell you here, look at this mechanical system and create the equivalent mass spring damper system, it really depends on how the system behaves. I don't know how many springs the system has, what surfaces create friction. If there is mechanical dampers inside, we need to analyze each system on their own and then come up with the closest approximation we can to recreate the behavior of that system.
Okay.
And that can take an undefined number of elements.
Professor, this is more like the mechanical things. How this one can relate it to the electrical part?
The electrical part we're going to start in the next lecture, and we will notice that the differential equations that describe the mechanical and the electrical are exactly the same. The only thing that changes are what you call, for example, a viscous friction coefficient here that dissipates energy. The equivalent element in an electrical system will be a resistor, which also dissipates energy. We'll come up with equations that at first glance look different, but when you compare them, they follow exactly the same structure. But instead of representing a mechanical system, they will be representing the electrical system.
Okay, thank you.
Okay. Any other questions? No? All right, then, that's it for today. I will have office hours from now until 12:30. I'll be on Zoom very shortly. I'll just close everything here. And if you have any questions, I'll be available on Zoom. The link to the office hours is different. It's posted on Brightspace. Okay, let me know if you have any questions. I'll see you again on Thursday.